And greetings. The title of this presentation is Inclusion of Rotational Inertial Effects and Power Consumption Calculations for Vibratory Pile Equipment. And this may seem like a fairly arcane topic, but given some recent trends in construction equipment, I don't think so. This is a topic which has kind of intrigued me for a long time. I've been designing vibratory pile equipment for 30 years now, and this is something that I think need, at least from my standpoint, to be put to rest. But also, given recent trends, I think our understanding of power requirements and torque in vibratory pile equipment is more needed now, and I think you'll see why when we get into the presentation. There's a DOI at the bottom for those of you who want to look up the paper behind, which actually explains all of particularly the math portion of this in detail. So, with all that, let's begin. Let's start with vibratory hammers in general. The operating principle is deceptively simple. There are paired eccentrics, and they're paired for a reason. If you rotate an eccentric mass around a shaft, you will get a force that varies with the direction of the center of gravity. Now, if you only have one of those, then you're going to have a force that will have both a horizontal and a vertical component. To eliminate the horizontal component, which is particularly important with pile driving equipment, we pair the eccentrics and we counter-rotate them, and the horizontal forces cancel out and the vertical forces add to each other, and we get a vertical sinusoidal force. And that vertical sinusoidal force then acts on the pile, which in turn acts on the soil. Originally, the vibratory hammers were developed in the Soviet Union in the late 1940s, they were first put out. But actually, that effort started probably in the late 1930s and went on into the 1960s. It was a major effort on their part, and they they pursued it very diligently, actually, and developed a wide variety of vibratory equipment, compactors, vibratory grates for conveyances and that kind of thing. The first, for pile driving equipment, the first job was in 1949 when the BT5 was introduced, and it had a dynamic force of 214 kilonewtons, an eccentric frequency of 41 hertz, and a power of 28 kilowatts. It was at the Gorky, which is now Nizhny Novgorod, hydroelectric development, and there were 3,700 sheet piles, 9 to 12 meters long, and they were driven each in 2 or 3 minutes. The performance difference between vibratory hammers and impact hammers in the right types of soils is significant, and is one of the reasons why this equipment has almost, for most types of soils that sheet piling is used in, has become been used for sheet piling. You also see them in soldier piles and other types of retaining walls. This is a diagram of the BT5 vibrator. It shows all the components so that you have the regular vibrator today are there. In the top, you've got the electric motor, which transmits its torque to the gears and eccentrics through a transmission system in the upper left-hand corner. In the middle, you have the eccentrics, and at the bottom, you have the clamp, which actually attaches it to the pile. The pile has to be attached in such a way that you get bidirectional rotation, bidirectional transmission of force. In other words, you've got up and down forces. It's not like an impact hammer where you just set it on top of it. You've got forces in both directions. The one thing that's missing from this that is more common now is the suspension. And that's normally, there are two reasons why you have suspensions. One of them is to provide extra down weight to help push the pile into the ground. And the other one is during extraction, you use it to dampen vibrations to the crane. Subsequent developments, they developed vibratory pile drivers for large steel pipes, which are still a very common application for them, square concrete piles, and concrete cylinder piles. Concrete piles are a something type of thing with these because of their large toe areas, which I'll get into. The first, the vibrator you see is a Soviet B402 pile driver, which has a dynamic force of 270 kilonewtons and a rotation frequency of 23.8 hertz. And they're driving sheet piles, and I think they were Larson types in St. Leningrad, which is now St. Petersburg. The first country that received vibratory technology was after the Soviet Union was Japan. They were licensed for it. Many of the Japanese machines imitated the Soviets almost slavishly in some cases. The one exception is the one you're looking at, which is the Uraga, which actually reversed the rotor in the stator and became, and it was a very unique machine. I mean, Vulcan distributed that in the early 1960s. Western European manufacturers like PTC in France, which is still active in it, and some in Germany like Mueller and MGF were also developed this type of equipment. One thing that is worth noting is that until the late 1960s, virtually all vibratory pile drivers were electric. There is a movement now to return electric equipment to the job site for purposes of getting rid of internal combustion engines and doing clean energy. And some people say this is very, very novel. In fact, it is not. We have done electrics with vibratory hammers for a long, long time. And I think that's something that needs to be remembered and that experience to be built on. In the United States, the hydraulic vibratories were first developed. The MKT developed the first one. You see a diagram of it in 1969. And then Foster and ICE, that's an International Construction Equipment 216 over there on the far right. Vulcan had a series back in the 1980s and 1990s, and Vulcan Foundation Equipment is once again bringing vibratory hammer manufacturing back to the area. We have HPSI and APE as well. There are basically three types of vibratory hammers based on their frequency ranges, low, medium, and high. What you're looking at there is a Foster 4200 unit, which Vulcan manufactured in the 1990s. On the right is basically the exciter. You've got the bottom is the clamp, and above the clamp is the gearbox where your eccentrics are. At the top is the suspension with the suspension springs. On the left is the power pack, a hydraulic power pack. American contractors have traditionally preferred a hydraulic hammer, and this is why they were developed in this country. The low frequency vibrators have usually around 5 to 10 hertz. They are used with high mass and toe resistance. Basically, the idea is to turn the entire pile into a impact ram that basically lifts up and beats against the toe. The largest of those in the Soviet era, I don't think in terms of eccentric moment anybody else has beaten this, is the VPM 170. It has an eccentric moment of 510 kilogram meters, but only a frequency of around 9.17 hertz. So these machines, there's a photo and a diagram of that. The Japanese use them, but are not very common today. Medium frequency vibrators are pretty much the standard. Those are two Vulcans 2300A and the 4600, which is driving a large caisson. Development of caisson driving for drill shafts revolutionized the construction of drill shafts in the 1970s when the larger vibratories were applied to it. This is the standard range. You have a nice balance of frequency, eccentric moment, dynamic force, and you can drive a wide variety of piles with these. The high frequency vibrators break down into two different types, the non-resonant around 40 hertz, 2400 RPM, and they're normally used not to vibrate structures around them so much. Resonant, actually, traditionally vibratory hammers assume that the entire pile acts as a unit, as a mass. Resonant frags actually put wave effects into the pile. They've had some acceptance. but they have not made the progress in the industry that I think some of their proponents would like. Modeling vibratory driving. For purposes of modeling, the simplest model is a dashpot, which is a velocity resistance type of thing. And for a liquefied soil, that makes sense. And it's traditionally been used to determine the power requirements for vibratory drivers. Traditionally, we've always assumed that the rotational speed of a vibratory driver is constant. Here, we're going to throw out that assumption. The reason why we can justify that is because the torque is constantly changing in a vibratory eccentric. And because of flywheel effects, because we cannot match the torque continuously all the time, for perfectly constant rotational speed is impossible. The question is that significant? And the purpose of this study is to get to the bottom of that. The governing equations are these. It's a system of differential equations. The first one is those of the eccentrics. I naught is the rotational inertia of the eccentrics. T is the torque, which we're going to assume constant. And K is the eccentric weight, which at any given point in vibratory driving is constant, even though there are variable eccentric machines. M is the mass of the vibrating mass of the system, the gearbox, the clamp, and the pile. C is the damping, which simulates the soil effect. And alpha T is the angle as a function of time. We can't assume that it's strictly based upon the omega or the rotational speed. First variable change, we're going to make three of them. The first one is to have a dimensionless time, and we'll talk about what W naught is, omega naught is in a minute. And that results in that transformation. Probably the most difficult from a mathematical standpoint, because the time is an independent variable. The second one is the pendulum frequency. Now you'll notice that photo shows two eccentrics, and you've got a crowbar jammed in place. And the eccentrics are actually, usually if they're, gravity will force them where those flats on the eccentrics will be horizontal, and they're up now. If you were to take and suddenly knock that crowbar out of place, the eccentrics will rock. And the frequency they rock at is the pendulum frequency of the eccentrics. And that can be computed based upon the properties of the geometric properties of the gears and the eccentrics and whatnot. And that is equal to the pendulum frequency is equal to that formula that you see, which is a function both of the rotational inertia and the eccentric moment. And you make that transformation, you get those. The last variable plays is a dimensionless displacement. We make that change and we get those. So now we've got a dimensionless type of formulation which we can use for parametric studies. We make some simplifying constant. Eta 1 is the torque ratio. Torque is constant, K is constant, so we're assuming a constant torque. The torque ratio is the ratio between the torque and the eccentric moment. Eta 2 is the damping coefficient, which makes dimensionless the damping. And 3 is basically the dimensionless expression of a peak acceleration, which we'll get into in just a minute. We make those transformations, we get that. We get those equations, which are a little simpler in form than the other ones. Let's do another simplification. Let's consider, you noticed in the omega naught is a function of both the rotational inertia and the eccentric moment. And we do a little math and we define an I sub k, which is the actual ratio, and then that ratio in turn determines the pendulum frequency of the eccentrics. And we can refine those ratios in that way. From there, we make some other simplifying. We have a zeta, which is equal to the C over M omega 1. Omega 1 is the actual target speed of the vibrator. And what we're going to define is a frequency ratio, which is equal to the RPM1. We're working RPM, it's a little easier to understand, over the RPM naught, which is the pendulum RPM of it. Is the pendulum frequency expressed as RPM. And we have N. Now, N is an important because it is the peak free-hanging acceleration of the machine. And so we have that. We make all those substitutions, and the ATIS suddenly are simplified considerably. And we can use these now that we have omega ratio as a parameter. So to solve the equations do not have a really good closed form solution, at least not in the form they're in. Use a four-floor Runnercut integration technique. Basically what we're going to do is we're going to vary the torque until we get the desired rotational speed, which is necessary since we have a variable RPM to start with. So we did some initial results, 1600 RPM, N is equal to 9, which is a standard value for design, and zeta is equal to 1. And the really surprise, even when we vary, the pendulum frequencies vary between 20 and 200 RPM, the results varied very little from if we had assumed a constant torque. As zeta decreased, the variation increased. In other words, the lower the load on the machine, the more variation in speed you have during rotation, which is good because obviously you want stability at the very highest rotational speeds. So that with that out of the way, that was a surprise. So we decided to expand to include the RPM values of 1,000, 1,600, 2,400 RPM. As before, the pendulum frequency was varied from 20 to 200 RPM. And we're going to vary the N value as well from 6 to 16. Is 9 is an assumption. What happens if we change that? At 1,600 RPM, we have this. Over on the left, you have the torque variation as a function of N and RPM, or actually that is the pendulum RPM, not the RPM it's being driven at. The RPM 1 is 600 RPM. And we see that we get a torque ratio variation of 3.5%. In other words, we're to get a reasonably constant rotational speed, the torque ratio varies a little bit. When you get to zeta is equal to 1 on the right, that drops to a little under 2%. So again, it's more stable in the higher load ranges. For 2,400 RPM, it's actually more stable overall. The further away that the rotational speed gets from the pendulum frequency, the more stable your rotation is, the more inertia there is. And by the way, I might add that at this point that the RPM range is based upon a fairly brief study, which I discussed in the paper, of various geometries of eccentrics and gears and whatnot. And I would say that very few vibrators currently on the market have a pendulum frequency much above 100. So that's an extreme high range of pendulum frequency. You go down to 1,000 RPM, you get quite a bit more. And the closer the pendulum frequency is to the operating frequency, the more wobble you're going to get during rotation. And that may explain some of the problems that they had with the lower frequency machines, why they were not accepted. Now some conclusions and observations. The velocity-dependent damping is a useful model as a design guide. It may not be effective in situations where you've got rock or IGMs, and as a result, some of the success of the American vibratory hammers, which are usually have a higher power, more power than some of their other counterparts elsewhere have been in the past, may be due to the fact that they are more effective in unusual situations. Higher acceleration than the user encountered during use, and that may be one reason why that is a problem. That actually higher accelerations are needed for whatever liquefaction or thixotropy is necessary during driving. The larger the spread between the pendulum and the operating frequencies, the less important pendulum effects become. As a rule of thumb, I think that the rotational frequency should at least 20 times the pendulum frequency, and most vibratory hammers achieve that. There are other sources of rotational inertia in vibratory hammers which will further stabilize the rotation. You can add inertia to the system. And there are other losses as well as far as need for extra power. This is not a large one. You've got losses in the hydraulic system. And if we go back to electrics, we'll have losses there too that are worth taking into consideration. So again, I thank you for your attention to this topic. And as I always say at the end of my videos, thanks for watching and God bless.